everybody for coming back to the second part of the first day of this workshop. And now we are going to move to the second contributed talk, which is going to be by Aaron Collavini. Aaron, you have half an hour to speak, and then we have the Q&A. So if you need me to stop you 10 minutes before to let you know that you still have 10 more minutes, let me know, but if not, just speak for the half an hour. Okay?
Okay.
So Aaron, the floor is yours. Yeah. Don't worry. Yeah. Thank you.
I sent an email to Andres. Maybe it will take 2 or 3 minutes more. So I'm
okay.
going. I start soon, so that I hope there won't be problems.
Okay.
So good. Here it is good afternoon, good night almost, but there it is good morning. So I'm Adam Collavini. I'm actually a PhD student at the University of Udine in physics and also at the University of Geneva in philosophy. So I'm actually doing a double degree in physics and philosophy. So the talk of today is about primitive ontology that someone already mentioned and cosmology. In particular, this is a case study based also on a paper published by Niels Martens and Dennis Lemkuhl of 2020. Was very roughly was consequences that in a sort of way we shouldn't anymore defend a sort of dichotomy between space-time and matter. So I'm seeing that through the lens of the primitive ontology and argue that that might represent a huge problem for the theory and maybe try to find some counterexamples. So this is an open work, so I'm open to your suggestion, to your contribution, because I will have to write a chapter on a book on Cambridge, for a book on Cambridge University Press. Therefore, every comment is accepted and welcome, especially. So, the goals of the talk. First of all, I will present the primitive approach to the ontology of physical theories, at least a reading of the primitive approach. Then I will analyze this case raised up by Martens and Lemkuhl about superfluid dark matter that might undermine this. Then I will compare the case with the lessons taken from the framework of analog gravity. And lastly, hopefully, I will try to see whether I can save space-time, and therefore I can save primitive ontology that is based exactly in this division between space-time and matter. So let me begin. First of all, let me start by talking about what are theories of physics in the first place. Well, the term physics comes from Aristotle's books, which is Physices Acroasis, which means lectures of nature. Therefore, for Aristotle, to specify the physics of an object is to specify its nature. In his case, in his particular case, okay, in this particular case, the physics come from the internal source of motion. Therefore, Aristotle says that, for example, air moves up, water goes down, fire moves up, rocks goes down, and therefore to specify the physics is to specify the motion. So for Aristotle, physics is matter in motion. And therefore, to specify again, physics was understood as involving two elements. One is matter, one is motion. And to specify motion, of course, you need to specify space-time in a way or in another. This was also, matter in motion was also the ontological commitment of Newton. So we are also talking about 2000 years of physics. Now the situation has evolved a little bit, meaning that it is not matter, but matter should be specified by what Bell defined the so-called local variables. Local variables are the ontology of the theory. Therefore, for example, I don't know, particles, it could be fields, it could be mass density, it could be flashes in the case of GRW. And also, in order to be variables, they have to be local. And in order to be local, it has to be space-time. So again, in order to define matter, you need also space-time, at least under this view. Then, of course, in quantum mechanics, the situation is a lot complicated. We already talked about that with the case of Bohemian mechanics. And we can also have non-local variables, for example, the quantum state associated with particles, or every variable that is non-local in general, and for example, gives rise to the non-locality that we already know about quantum mechanics. Therefore, it seems to be that a clear theory of physics, at least under this reading, I am being influenced a lot by Tim Moldin, which was also my supervisor. So the recipe for any clear theory of physics should specify what? First, the ontology. So what is there? Particles, fields, whatever there is. And in order to specify the ontology, I have to specify local variables, non-local variables, and space-time, because space-time has to account for the dynamics of local and non-local variables. And after the ontology, I have to specify, of course, the nomology. So what the ontology does. And this, of course, gives me the dynamics. So the nomology is, we are talking about laws. And laws are evolution through space-time of local and non-local variables. We can also talk about primitive and non-primitive variables to specify the primitive ontology. This is maybe the more common reading of what is primitive ontology, but now I'm focusing just on Tim's way of reading. Even if I don't think Tim agrees completely on Valeria Lodi's specification of primitive ontology, but at least this is at least a clear general future of what has to be primitive ontology. So, the question is primitive ontology viable in cosmological theories? Well, it appears so. Let me just, for example, in cosmological theories, we have the lambda CDM model. We have already talked about that today. The lambda CDM model postulates ingredients, of course, space-time, described by the Einstein equations. It postulates the existence of lambda, which should be dark energy. Right now we don't really know what is to be lambda. It should be vacuum energy. It should be a constant of nature, or maybe it is, I don't know, it is associated with quantum field theory. We still don't know yet, but at least it has to be something in space-time, in a way or another. So we still need to understand it better, but at least we know that it must be in space-time. Also, other than that, we have, of course, candidates for cold dark matter. And we have, of course, even here a lot of candidates. So this is just an example above a lot of examples that you can find. For example, you have a supersymmetric WIMP, weak interactive massive particle. It has an equilibrium cross-section. It has a self-interaction. It just contributes to the 27% to the total cosmic mass energy budget. So at least we can postulate the primitive ontology of a cosmological theory, but tell that, okay, there is space-time, there are this energy field, and there are, for example, particles. Particles that are associated with cold dark matter. So at least it seems straightforward to individuate the ontology and the nomology in cosmological theories. Well, there is a problem raised by Martens and Lemkuhl. This problem is associated with the superfluid dark matter. In general, what is the problem? The problem is that in this superfluid, and I will tell you about in a minute, there is no clear distinction regarding the fluid, whether it is matter or whether it represents a case of modification of space-time. And I will talk about this now. So, the theory of superfluid dark matter was proposed by Beresiani and Curie in 2015 and 2016. And it has a very, very good future, since it incorporates both future for dark matter and modified theories of gravity. Right now, we know that modified theories of gravity work better at the level of galaxies and not so much at the level of galaxy cluster. Whereas dark matter does the opposite. So it works better at the level of galaxy cluster and not very good at the level of galaxies. So they propose a model that does both with just one element, it appears, which is a superfluid dark matter. This is a matter field that is postulated, that is dark matter field, it is represented by the function phi, and here it has also a Lagrangian formulation, a clear Lagrangian formulation with parameters that are added, of course, ad hoc in order to guarantee some physical features. One of these features is that below a temperature, or analogously over a length scale, the de Broglie length scale of the particles of the fluid, at the level of galaxies, there is a symmetry breaking. This symmetry breaking makes this dark matter field to behave as a Bose-Einstein condensate. This Bose-Einstein condensate can be seen as proportional to epsilon that contains a theta term, and the theta term, this theta term in particular, is nothing but the phonons of the fluid, because these phonons cohere and mediate a sort of force. Therefore, again, we have this dark matter fluid, and we have below a certain temperature that it behaves as a condensate. This condensate has phonons, which are nothing but quantized sound waves, and these sound waves enter into the equation of motion, and they mediate a Mondian force. A Mondian force is nothing but a modification of the space-time structure. So with one field, you can recover also the futures, the positive futures of modification of space-time. So let me just talk a little bit more about phonons, represented again by the function theta. So these phonons, as I said, mediate a modification of space-time. This modification can be seen in a further term that is added to the theory by Beresiani and Curie. And this term is as a form inspired by tensor vector scalar theories. These theories, you can see it straightforwardly, that they consider also not a metric G, but an effective metric G tilde. And psi of alpha represent the luminous matter fields. You can just see that the effective metric depends on, other than the standard metric of GR, on theta, which are, of course, again, the phonons of the superfluid dark matter. So phonons enter into the metric by modifying the already existing metric of spacetime. So this seems that these phonons act also as a modification of spacetime. An important modification, because in this term that they have added into the equation of motion, the psi of alpha represent all luminous matter fields. Therefore, all fields follow equations which are coupled to this effective metric, and also they are specified by covariant derivatives that are defined with respect to this metric. Therefore, it seems that all fields follow the effective metric that has that depends on the phonons of this superfluid dark matter field. So this might represent a problem, right? Because for Beresiani and Curie, for Martens and Lencourt that analyze their case and that enumerate a number of criteria for matter and spacetime, they just conclude, at least they published two papers, but two very great papers, but at least they argue that there can be some conclusion by which we can resist a dichotomy between matter and spacetime and maybe treat them as a unique ontological entity. So we should no longer defend a dichotomy between matter and spacetime. This is their general conclusion, or at least it can be concluded from some of their conclusion. Sorry for the repetition. So this, in the way I've explaining to you primitive ontology, it represents a huge problem, because primitive ontology starts by defining what is to space-time, to be space-time, and what are matter on it, what is matter on it. This is the first, and these are the first elements that goes into the ontology. Then, of course, you need the nomology that specifies the dynamics. But at the very beginning, the ontological ingredients are space-time and matter. And if we don't have this clear division between matter and space-time, well, the primitive ontology, which, by the way, for me, it is the clearest approach to physical theories, might have a huge problem and might fall down. So my aim is try in this last part, okay, I still have time, to try to say primitive ontology. And the way I'm doing that is to consider the case of analog gravity. So, first of all, let me just specify my very question at the beginning. The key point of all is this: does the existence of an effective metric, which is G tilde, which was the effective metric that has also the phonos, the contribution from phonos inside it, really imply that the manifold equipped with this metric represents a spacetime? Because this is the underlying assumption, of course, of Matter and Lempool, and from this it follows that if that represents spacetime, then the dark matter fluid should also be considered as an aspect of spacetime. Well, this is, I will try at least to argue against it, or will try to provide some motivation that we can at least in some way resist this assumption. And I will do that by taking the case of analog gravity. So, for those of you who doesn't know, analog gravity is a search program that explores analogs of gravitational fields with other physical systems. For example, these systems are generally condensed matter systems, and the aim is to gain new insights into related problems. In particular, analog gravity individuates several sharp analogies by which it is possible to probe aspects of physics of curved spacetime, in particular to probe aspects of curved spacetime quantum field theory. This is something, let me stress this from the beginning, that is analyzed in the laboratory. So we are not talking about idealized case. They are really building analogs of black holes called, for example, sonic black holes or dumb black holes in the laboratory. So in this way, they are trying to see analogs of, for example, Hawking's radiation in the laboratory, and therefore they're trying to analyze better some feature of space-time QFT in curved space-time. And this aspect, of course, are describing by introducing an effective metric, of course, because we are trying to analyze curved space-time aspects. So this is, for example, a case, acoustic of a moving fluid. The key point is this: they consider a fluid that has its background flow represented by phi of 0. In this background flow they consider Lorentz acoustic disturbance that goes around it. And they found that under central conditions that are arguably good, you can describe the dynamics of the acoustic disturbance over the background flow by a minimally coupled, in the same way of a minimally coupled massless scalar field propagated in a general 3+1 dimensional Lorentzian geometry. So what they do is that the dynamics of the disturbance, the acoustic disturbance in this flow, has the same form of a scalar field in a Lorentzian geometry. This geometry is defined with respect to this metric that is exactly an effective metric. In this case, it's called an acoustic metric, G of 0 mu nu. And this metric is a metric associated with the background flow. So, in particular, this metric contains terms that depends on the density, the velocity of flow, the local speed of sound of the fluid. And this metric defines, of course, an acoustic-like element. This line element should give you, in a sort of way, the sort of distances of this analog space-time. But more importantly, it specifies the dynamics. Also, since it is a line element, this line element defines sound cones. So sound cones are defined, and since And since the metric is defined with respect to the velocity of fluid, a supersonic velocity, as you might see on the right, forces the metric to select a tilt and restricted sound cones that is followed of by the acoustic disturbances. So the disturbances have to follow this causal structure. Okay, so it seems from this point of view that we are really talking about an aspect of space-time. So let me just highlight some analogies between this analog gravitational case and the superfluid dark matter. So in both cases, we have some arguably more fundamental fields, which are the background flow and the superfluid dark matter, that live in a standard relativistic spacetime. In the first case, we have a Minkowski metric. In the second case, we have the metric of Einstein, the standard metric of general relativity. These metrics are in both cases modified by terms that are associated with the medium, which are velocity terms. In the first case, the velocity of the medium. In the second case, the velocity associated with the superfluid dark matter field. In both cases, we have matter entities, which is in the case of analog gravity are perturbations, and in the case of superfluid dark matter are luminous matter fields, that follow paths that are determined by the effective geometries. So even this is analogy, a strong analogy. And also, in both cases, equation can be derived from a general Lagrangian formulation. These are analogies. Of course, this in a sort of way seems to be a weaker case, because the important thing about the superfluid dark matter is that all luminous fields follow this effective metric, which is not, of course, the case in analog gravity. In analog gravity, you just have the perturbations of the flow that follow this effective metric. So you don't have the metric that finds structure to be universal. I don't think this is really a problem, because right now I'm focusing on theories of gravity with torsion, but I can talk a little bit about that just at the end. Let me try to investigate whether the metric can be considered as an aspect of space-time. Well, we have the first counterargument is that it does not recover the real distances given by the spatial-temporal background of the laboratory, meaning that if you take the effective metric and if you just measure, for example, a distance, the distance given by the effective metric does not correspond to the distance of the laboratory. So this metric does not recover the distances, but it just recovers the causal structure, so the structure of sound cones. This might be a counter-argument. I will later argue whether this applies to the superfluid dark matter case. Well, also, the components of the analog metric depend on velocity terms with respect to different background structure. This structure is the structure of the laboratory, the metric of the laboratory. So there is also a dependence relation that cannot be eliminated, because if the fluid has zero velocity, or if the velocity changes, there is no change in the metric of the laboratory, at least locally. There is no change at all. But vice versa, if we change the geometry of the laboratory, so if we put the laboratory close to a black hole and we define a new curve metric, this curve metric will affect the dynamics given by the effective metric. So it will affect the dynamics followed by the linearized sound waves of the fluid. So there is this dependent relation by which one metric seems more fundamental than the other, and the other maybe it is maybe not a metric in the real sense. This is the third motivation, the more important one, by which there is a physical explanation of why disturbances follow the effective metric. And this is given exactly by the paper about analog gravities. It is explicitly said that a moving fluid, and we are talking about the background fluid, will drag sound waves along with it. And if the speed of the fluid ever becomes supersonic, then in the supersonic region, sound waves will never be able to find their way back upstream. This case is similar to the case of a leaf going over a river. You know, the leaf is on the river, if the river goes down, the leaf is first to follow the curves and the I don't know, the geodesics in a sort of way of the water that goes down. You never see a leaf that goes in another direction because the river drag with it all leaves that are in in the river, over the river. Sorry. And so this is also a similar motivation for the existence of dam hole, because if you have sound waves that go at supersonic velocity, then of course sound waves are not able to find their way back. They are not able to go against these sound waves. So this is a physical motivation that I think it is important. In this last part, let me see whether these counterarguments apply to the superfluid dark matter case or not. Well, the first counterargument was that the analog metric does not recover the real distances. But just recover the causal structure of space-time. Is this the case? So if I measure with a ruler in superfluid dark matter, does it give me the background metric, or does it give me the Federic metric? But, well, this counterargument does not apply to the case of superfluid dark matter. Because what is the problem? Because the Federic matrix is coupled to all luminous matter field. What does this mean? This means that if I take a ruler, this ruler, which is composed of electromagnetic fields, will be coupled to the Federic metric, and therefore the distances that I'm going to measure are the distances given by the Federic metric. So this counterargument does not apply. However, this universal coupling that seems to be necessary for space-time to be space-time. So space-time is space-time. This is the weak geodesic principle. I don't remember exactly. If all fields follow the same affine connection or metric connection. Well, right now I'm focusing my study on torsion gravity, and I'm realizing that with torsion gravity, no one is following anything. And so, for example, electrons do not follow neither the affine connection nor the I don't know, the metric geodesics. So this fact that you have to have this universal coupling might not be necessary for space-time to be space-time. Also, the effective
Aaron,
term
you have something like 3 minutes.
Okay. 3 minutes, even with 5 minutes. Okay, sorry. So the Federic metric is added ad hoc, and it is not easy to select which metric and fine structure is followed by particles, because this depends also on the stress energy tensor, and we have two stress energy tensors, so it should be seen experimentally whether one is right or not. And lastly, a following theory by Beresian and Curie breaks the coupling with phonons by letting them to follow geodesics defined by the standard metric and not the effective one. Then, the second counterargument, the components of the metric depend on velocity term. As we have seen, this applies in a straightforward way to the case of superfluid dark matter, meaning that the Federic metric depends on terms that are defined with respect to a different background structure. This background structure is the structure of the space-time whose metric is defined by the Einstein equation. Again, even here we have a relation that is asymmetric, meaning that if I change the superfluid dark matter, it does not affect directly the metric of space-time, at least if we do not consider, for example, the Einstein equation locally. But again, if we change the background structure, this structure will change and will affect the dynamics given by the Federic metric. So this is again a difference between the two metrics. And lastly, and I'm concluding my speech, there is a physical explanation of why the disturbances follow the Federic metric in the case of superfluid dark matter, of why luminous matter field follow the Federic metric. Because there are phonons. These phonons cohere, and they mediate, it is stated explicitly, a long-range force. So I think that in the same way of water that forces leaves to follow the flow of the river, we have phonons that force all luminous matter field to follow different geodesics. But this does not mean necessarily that we are talking about a different spacetime. So my conclusion are that we have two metrics in the case of superfluid dark matter, but only one has velocity terms that depend on the other, and only one can influence the other immediately as a real background, but not vice versa. And lastly, there is a physical reason by which the Fetric metric summarize the dynamical role played by the background fields, meaning that there is a dynamic, there is a force that justifies a modification of the metric like it was a real metric of spacetime, even if it is not. And such dynamics, by the way, it takes place only in the background field. And lastly, a substantivalist would still like to claim that spacetime is what remains if we remove our fields. In the superfluid dark matter case, if we remove the superfluid dark matter, what remains is just Einstein fields or Minkowski fields. And the Fetric metric just reduces to the standard metric of spacetime. So this, to conclude, if these arguments are sound, then we can say primitive ontology. Primitive ontology is nothing but the usual spacetime, dark matter field, luminous matter field, and theta, which are phonons, are just part of the non-primitive ontology of the theory. And with this, I have concluded my speech.
Thank you very much. Please, let's thank the speaker, reaction button. Yes, a round of applause. And now let's move to the Q&A. Yep. So questions, remember, raise your hand in the reaction button and raise hand. So let me check. Meanwhile, may I ask you a question, Aaron, to begin? I was wondering about how possible it is to extend the idea of using primitive ontology for other cases that are not analog gravity models and that have like more fundamentality type of a spirit, like the scalar field dark matter model, right? Because I think the problem there is you might have different primitive ontologies for different models. So either you are going to weaken your commitments towards that ones being more fundamental than others, like more certain in a sense, or you are going to decide that only primitive ontology might help as a methodology, but would tell us nothing actually about the ontology of the models, or you would have like a pluralistic type of outcome. Do you have any take on this?
Well, thanks for the question, first of all. Well, it doesn't undermine the primitive ontological approach. It just states that we are not sure about what is the ontology, the primitive ontology in the first place. I can do the same, for example, with the electromagnetic field. There are some papers that argue that, for example, in Maxwell theory, we have particles, for example, electrons, plus electric and magnetic fields. There are other philosophers that instead argue, well, the electric and magnetic field are not real field after all. They are just, I don't know, future that enters into the laws. They are not actual in the real world. Well, what is real are just, for example, electrons. And electron and magnetic field just enters into the equation and just force electron to move in a way or in another. So this is also a case in which you can try to give two primitive ontologies. And you can say the same, for example, in quantum mechanics, whether GRW, whether Bohemian theories. But the fact is just one, that at least you have a clear theory of physics in which you have space-time, and you think, for me, what is fundamental are electron or electron plus electric and magnetic fields. So the point is that at least to specify a clear theory, you need to specify the ontology. And then, of course, it is subject of philosophy to argue what is fundamental and what is not.
Thank you very much. A quick follow-up, because I do agree on your take on how to see primitive ontology, but I have the impression that not the large majority of philosophers of physics would agree on not having necessarily like the strong commitment towards what you call the ontology of each theory. Because as far as I understood your answer, what this primitive ontology addition gives us is more clarity about which are the basic elements of our theories without saying that there is a connection within the world or within the theories themselves, within different theories. And so in the case of cosmological models, it seems to me that there are models that in a sense are either more entrenched or more privileged, like SFDM, for instance, that it's considered to be fundamental. And so when you use primitive ontology in those cases, it might just say, well, these are the basic elements, and these are the basic elements of the other one. But it's just a clarity, like a conceptual clarity for philosophers to discuss, or is there any, like, a stronger outcome in terms of ontological commitments that we should inherit from this?
Well, first of all, I think that primitive ontology, I believe that in a sort of way, the majority of physicists do not care at all about primitive ontology, of course, but the good ones are really doing primitive ontology in a sort of way, meaning that you told me about, for example, the connection between what is there, what we see, right? Primitive ontology grew up exactly to answer this. For example, there are physicists that just say, okay, quantum mechanics is about the wave function. But the wave function lives in Hilbert space. Hilbert space is not here. And therefore, how do you justify what you see during experiments? And so primitive ontology gives the motivation and gives the tools to just, how can I say, to just give an example or to just explain that at the end, whether you are considering very different theories of physics, at the end you see something in space-time. This something is matter, whatever it is, and this matter has to be accounted by, I don't know, particles and waves, fields, and so on and so forth. The case of superfluid dark matter is this statement, because superfluid dark matter, in the way Barisian and Curie stated that, it is just space-time plus a superfluid dark matter. The superfluid dark matter enters into the primitive ontology. So there is a primitive ontology, just space-time given by GR, superfluid dark matter, and matter fields. So in the case of Barisian and Curie, they are exactly providing a sort of primitive ontology, and they think that the modification of space-time is just a sort of, it just emerges. Well, they are physicists, they are not philosophers, so the concept of emergence is a vague one, but at least they think that fundamentally the theory states that there is superfluid dark matter, matter fields, and space-time. So it is a primitive ontology, right, from this point of view.
Thank you very much, Aaron. Sergio, please.
Yes, thank you, and thank you, Aaron, very much for the presentation. I have one question concerning ontology, and the definition of ontology as what there is seems like a, let's say, a Quinian point of view, right, for ontology. But there are many other conceptions around or about ontology. You just mentioned Aristotle, you know, and or we have also Heidegger, right? So
Yeah.
my question is this election of ontology, is this conception of ontology as what there is it an election, or why in other terms, could one base this discussion on other ontologies or other conceptions of ontology?
Oh, well, this is a good question. I think you can do that. I think you can do that. But of course, this ontology in particular is motivated by scientific instances. So of course, people that are defending primitive ontology, they are defending a view by which all there is about the world is related to physics and to what we observe, right? So I think you can have different kind of ontologies, but at least those people reduce the ontology only to what there is. I make you just this example just to tell you what kind of people are about. So one of the defenders, even if it is not primitive ontology, but I mention him, is Tim Maudlin. In his book, Metaphysics Within Physics, Tim Maudlin just states, metaphysics is ontology. Well, for those of you who have studied metaphysics might be in part ontology, but it's not only ontology. But for him, he just reduced everything to what theories of physics seems to tell about the world. So he's reducing everything to this small conception about ontology. Okay, I think you can extend it, but then you might have other motivations that are different from mere physical motivations. This is what I think. I don't know whether I answer you or not.
Thank you very much.
Thank you, Sergio. Thank you, Aaron. And let's move to the last question, which is coming from Facebook and says, it's also in the chat. Much of the motivation for primitive ontology relies on a clear distinction between primitive and non-primitive variables. But in cases like SFDM, where matter fields effectively determine a space-time structure, do Motley's type criteria still provide a workable guide, or do they risk reimposing distinctions that the physics itself no longer supports?
Well, this is exactly the point, right, of the presentation. This is exactly the point that Martens and Lemkuhl tries to raise. They raise the fact that maybe we don't longer need this distinction between space-time and matter. I myself believe that we still need it. And I myself think that since I'm a privileged ontologist right now, maybe in a couple of years I will change my mind. I don't know. I'm also a philosopher other than a physicist. But the point is that we have to be careful when we think that matter and space-time are the one and the same. And I wanted just to tell you, there is this citation in Tim Modin that says we can even think about the categories that melt, so that space-time and matter are no longer distinct, but it states that in a clear way. Maybe I can read that to you. Let me just give you one moment. But I don't know. Well, I can state that just directly. But in some cases, we need the distinction to render theories of physics clear, because we can, describe everything, but at the end, what you see is just always matter moving in space-time. Of course, this view is against string theory, is against all theories that try to quantize space-time. If you talk with Tim's modeling, Tim gets angry about this because it doesn't know what is to quantize space-time, and what is to say that space-time is not fundamental. In part, I agree with him, but at least you have to recover something in space-time, because experiments are done in space-time, and there is no clearer way to do this other than, I think, primitive ontology.
Thank you very much, Aaron. And if there are no more questions, let's thank the speaker with another round of applause in the reaction button. Thank you very much, Aaron. And
thanks so much to everyone.
Thank you. And remember that the talks are going to be recorded and hosted through the YouTube channel of the Institute for Philosophical Research at UNAM.